Morning. Today we're going to look a little bit more at probability. Now, there's basically two ways that events can interact. They can be independent events or they can be dependent events. What we're talking about right now is independent events. Now, an independent event or independent events, because we have to have two things to know whether or not they're going to be independent of each other. Independent events don't affect each other. It would be like me rolling a die, and it would be like you flipping a coin. Well, clearly those two things are not going to be related. Whatever I get, if I roll a 3, that's not going to affect whether you get heads or tails. Those are independent events. There's lots of independent events. In fact, if I roll that die and get a 3 and pick it up to roll it again, whatever I just got the first time, that 3 is not going to affect the second time I roll that die. Every time you roll a die, it is a new event that is independent of the ones before it. Now, dependent events, and we'll talk more about dependent events in one of the next videos, but dependent events do affect each other. Okay, that's like the classic example of a bag of marbles, or let's say you have a bag of Skittles, right? There's all kinds of different colors of Skittles in there, red ones and green ones and blue ones, and the black ones or the brown ones that you shouldn't eat because they're probably old. But if you have all the Skittles in there and you pick one out, right? And there was some probability that it was going to be green, right? Maybe you got a green one and you ate it. Well, that's now affected the probability that you grab, or it's going to affect the probability of whatever comes out next, because there's now less of a sample space in there. There's less things to actually grab at. It's going to affect the next probability, okay? So it's like that. You took something out and you didn't put it back in. We'll talk more about dependent events soon. So independent events, two events are independent if and only if their product, two events are independent if and only if the probability of them happening together is equal to their product. Okay? The probability of two events happening together, if it is their product, then they are independent events. So we are told here that all events A, B, C, D, and E are independent events. And we want to find each of these things here. First, we want to find the probability of A and B. Well, since we want to find the probability of A and B happening together, both things happening, and because A and B are independent events, we know that's going to equal the probability of A times the probability of B. It is that simple. So that would be 0.3 times 0.6, which gets us 0.18. That is the probability of both of these independent events happening together. Probability of C and B, well, that would be the probability of C times the probability of B which gets us 0.33. The probability of A, B, and C all happening, well, that would be the probability of A times the probability of B times the probability of C and that gets us 0.99. Which leads us to this last one here. We want to know, what is the probability that E happens all by itself? And we're given that the probability of A and E, both independent events, the probability of them happening together is 0.225. Well, if they're independent events, the probability of E times the probability of A would have to give us the probability of A and E both happening. Well, let's plug in the values we do know. We don't know the probability of E. We do know the probability of A. That's 0.3. And we do know the probability of A and E happening at 0.225. So to get the probability of E, we can divide both sides by 0.3. That leaves us with the probability of E, and 0.225 divided by 0.3. Probability of E comes out to be 0.7534. So again, independent events, two events are independent if and only if the product of their probabilities is equal to the probability of them happening together. Okay, so we want to, again, find the probability of some things here. We want to find the probability of choosing a jack from a deck of cards and rolling a number less than 6 on a die. Well, notice how these events are independent. We need to be able to recognize when two events are not going to affect each other, and choosing a jack from a deck of cards isn't going to affect what you roll on a die. So, probability we choose a jack from a deck of cards, that's 4 out of 52, 1 out of 13. Probability of rolling a number less than 6 on a die, well, that would be 5, 6. So we multiply that. Multiply across the top and get 5. Multiply across the bottom and get 78. That's not going to reduce. We can leave it just like that. 5/78. That is the probability of getting a jack in a deck of cards and rolling over. That's the probability of both of those things happening. The probability of spinning a 2, notice our life wheel over there, probability of spinning a 2 and flipping heads on a coin. Well, spinning a 2, there's 1 2 out of 10 equal regions on that spinner, so that would be 1/10. Flipping heads on a coin, that's 1/2. So the probability of these things both happening would be 1/20. All right, here, experimentally, Chipper Jones has got a hit 31% of the time he is up to bat. What is the probability he gets 3 hits in a row? All right, well, when he gets a hit, it's not going to affect what's the next time he gets. It's not like when you're playing baseball, you say, I got a hit, I'm definitely going to strike out the next 3 times. That's not how it works. When you get a hit, you come back up to bat, depending on how good you are. In the case of Chipper Jones, 31% of the time he gets a hit. So you know what? Next time he's up to bat, he still has that 31% chance that he gets another hit. So what is the probability he gets 3 hits in a row? Well, that would be 31%, 0.31, times 0.31, times 0.31. He gets a hit, he gets a hit again, he gets a hit again. What is the probability that this does happen? Zero 0.0298. To make sense of that, 2.98% chance that he actually does get 3 hits in a row. So when he does, get a 4-hit game or a 3-hit game, that is really impressive. If you have 1/4 the chance of randomly picking the right multiple choice answer, what is the probability that you randomly pick and miss 3 in a row? What is the probability that you miss? If you have a 1/4 chance of randomly picking the right multiple choice answer to miss the answer, you have 3/4 of a chance to miss that question. So you miss it once, that was 3/4 chance. Well, you might miss it a second time, and you might miss it a third time. And if we multiply these together, 3 times 3 times 3 is 27, 4 times 4 times 4 is 64. That will not reduce, that is 27/64 chance that you actually miss 3 in a row if you're randomly guessing, and if it's a 1/4 of a chance for you to get it correct. 27 out of 64, that's about 42.2% if you're randomly guessing 42.2% chance you miss all three of those. All right. Independent events, that's what we're dealing with today. That was all that was. These were independent events. Every time something happened, the next thing we're looking at wasn't affected by the previous thing. Okay, one more thing I want to look at with independent events. Here, they gave us some information we know about probabilities of A, B, and C, and they want us to actually determine if these events are independent based on the information they give us, okay? So remember what I said earlier. Two events are independent if and only if the product of their individual probabilities is equal to the probability of them both happening. So we can use that to check. Right here, we see the probability of A and C is 0.165. Well, if that is true, if these are independent, okay, and the probability of A and C is 0.165, then when we multiply the probability of A, 0.3, times the probability of C, 0.55, if they are independent, it should equal 0.165. And so we should check that. 0.3 times 0.55, and that gives us, that does work. 0.165 did equal 0.165, so these are independent. Yes. Are they independent? Yes, they were, because that did work out. Here, the probability of B and C is 0.43. Are they independent? Well, let's check. The probability of B is 0.6. The probability of C is 0.55. And when we multiply these together, this comes out to be 0.33, not 0.43. Are they independent? No. Because the product of their probabilities did not equal the probability of them both happening.